Hey everybody, welcome to physics. So now that you've hopefully, tried some stuff, I'll tell all the, short and easy answers, which is probably what you're used to. But anyway, so what are we talking about? Well, the first thing that you have to absolutely know, okay, so you got a circle, and this here is called the radius, right? And circumference in meters is 2 pi radii, right? And that's that distance around the circle at a certain radius from the center. Okay? And then the other thing we got here is, something about like that, this arc, or this angle. So this angle is called a radian. And each circle has 2 pi radians in it too, or we could call it rad. This is kind of the short for that. Okay, and it just so happens that 1 radian is approximately 57.3 degrees. So everyone knows what degrees are, right? So 57.3 degrees. That's 1 rad, approximately. But here's the cool part about these two things. When we actually sweep out 1 rad of an angle, or 1 angle measurement rad, then because the relationship to rads and radius, the ratio is the same to a complete circle, and divided by 2 pi, we can say that an arc length, so this would be called arc length. So if you would make this into a straight line, the arc length, when sweeping out 1 rad, equals 1 radius in measurement, or in meters. Okay, does that make sense? So, if this radius here is 2, when I sweep out 1 arc length, this distance is 2. Okay? So, how does this work into, the first question I asked is, what is my velocity tangential? Okay, and I'm talking on constant circular motion or harmonic circular motion, which means that I maintain the same speed around the circle, so a constant speed. Okay, so when we have a constant speed or constant centrifugal motion, does it make sense that if we have our angular velocity, which angular velocity is rads per second. If we multiply that by the angle, or by the radius measurement, okay, does it make sense that we would get a meter per second? And does it make sense that it would be the actual measurement of how many meters are swept out per second? So to reiterate, what I'm talking about is, all you have to realize is 1 rad sweeps out 1 radius in distance. So if I have a rating of how many rads per second, like if I have 1 rad per second, and the radius is 1, well, that means my arc length that I sweep, or the distance I travel in 1 second, is 1. Okay? But if I have an arc length, or a radius of 2, and I'm saying that I'm sweeping out 1 rad every second, okay, my arc length then is going to be 2 meters, or my distance. And since, and that's per second. You know, because my angle measurement, or my angle displacement, or my angular velocity is per second, and this just becomes a flat, straight over meters per second. Let's look at this again, a little bit different way. So, because ultimately we're talking about the space hotel, right? And way down here is the Earth, and way out here is the space hotel. And what they have in common is they sweep out the same angle per time. So they both have the same angular velocity. Just for this problem, we're going to say that the angular velocity is 1. Okay? So we're going to say that the given for this is 1 rad every second. Okay? So you could think of a rad as a percentage of a circle, too. Right? But it's really an angle measurement. Okay, so here on Earth, I go 1 rad every second. Out here, I go 1 rad every second. But there's going to be a difference in the actual speed. Do you agree? Because I am traveling that distance in 1 second, and I'm traveling that distance in 1 second. So even though my angular velocity is similar, my actual speed is different. So, how would that work out? If we have 1 rad per second, and I say that, well, geez, I'm out here at, I'm just going to say 2 meters, and I'm over here at 7 meters. That's my radius, keeping in mind that this radius and rad is now interchangeable. Kind of. Even though one is an angle, one is a distance, the ratio to the circle is the same. So I can say, well, my velocity tangential at 2 meters is equal to my angular velocity times my radius. So that's how far I am from the path, or from the center of the path, right? So my velocity tangential at 2 is 1 rad every second, and my radius is 2, so my actual velocity is 2 meters per second. Now, I think maybe you actually got this understanding, and maybe it wasn't quite as neat of a package, because I know we had some trouble kind of explaining it so easily, but that's okay. The good thing is you're going through that thought process. So out here, my velocity tangential at 7 meters is the same formula, but my radius is different. Keeping in mind my angular velocity is the same, which is what we need to have that geostationary orbit, right? We have to sweep out the same angle. So we are maintaining, because really, if I'm sweeping out the same angle, then anything on this radius is going to be in line with anything else on this radius throughout the whole motion, right? So they used to have ice skating rinks, and roller skating rinks, long before too many video games and stuff. And you would do this thing called crack the whip, and this would be the head of one person, head of another, and you'd be trying to maintain the same angular velocity, and so your hands would be outstretched. Okay, and that tension was then the force centripetal keeping you on the circular path. So this guy had a good time, right? Because as long as I didn't get hurt, this person is the big, heavy one that is the strong one, kind of creating that tension between the hands. This guy's cruising along faster than he could ever go by himself. This guy's slow. Maybe this guy is going a little faster than he could do. It's kind of a hard thing, but it was fun. Who ever played that? Okay. And good. Okay. So, maintain the same angular velocity at 1 rad per second, at a distance of 7 meters from the center of the centripetal motion, we can see that our tangential velocity is 7 meters per second, which means I'm going a lot faster. So, thinking back to geostationary orbits, we said, if you think of this as the top of the Earth with looking down, we said at the equator we're going something like 460 meters per second or something like that, right? Which we're going to be able to determine with that our angular velocity, which I think we could do this a different way too. Is this guy going to have to, the space station or the space hotel going to have to go faster or slower to maintain that same angular velocity? Faster. Okay, so does that make sense? Any questions about that? Okay. So, what else? That's the big story. That's like what I really wanted you to get and understand. That's what I expect you to explore with your job. You should have 5 or 6 data points. Some of the other stuff, like angular acceleration, is just change in angular velocity per time. Kind of, I mean, you know what acceleration is? The same thing except for its angular velocity. I'm not going to spend a lot of time with it. I'll ask questions if you want later. I think that might be it, though. Now, the worksheet, of course, I didn't do tons of example problems because I don't do that. That would be the next step if you can't figure it out on your own now. So, what I'm going to have you do now is try that lab. And you've created it already or talked about it or thought about it. And then tomorrow we can revisit the worksheet if you haven't figured it out yet. The answers are actually online now. So, okay, hopefully that helps.